Excellent.
Okay, thank you. Thanks a lot. I'd like to thank the organizers for giving me the opportunity to give a talk here today. So as the title says, I'll give some motivation and a way of connecting classical and quantum integrability, so classical and quantum integrable models. So to start with, I'll give a plan of my talk. So I'll start by giving a classical integrable PD, so the Sinch-Gordon equation in particular. Then I'll show you a way of connecting the Sinch-Gordon equation to the Schrödinger equation, which is an ordinary differential equation. And then I'll talk a bit about this curious ODE-IM correspondence, which actually will lead the way to the connection with quantum integrability. So I'll start off by talking about the Todd equations. So Todd equations, it's a simple example, not a simple example, it's one example of a system with nonlinear interactions. So we have a chain of particles. Actually, I've considered here a periodic chain. Oh, sorry. A periodic chain. So it's n particles interacting with this exponential interaction. And phi n is the displacement of the nth particle from its equilibrium position. So we can write, over here we have a system of ODEs, and we can write a two-dimensional continuous generalization of this model. So we can write it like this. So essentially we can write a system of PDs, where phi is the field and it takes real values, and so is x and t. So an example, the simplest example of Todd equations is if we take the number of particles to be 2, and if we also impose this condition, so phi 1 being equal to minus phi 2, then we obtain the Sinch-Gordon equation. Now if we set x and t, if we transform x and t to z and z bar, so it's the so-called light cone coordinates, we can rewrite the Sinch-Gordon equation like this, where here by z bar I'm denoting the partial derivative. I'm just writing it in this form because it's cleaner. So why should we study the Sinch-Gordon equation? So it's a partial nonlinear differential equation with many interesting properties. So first of all, it has a rich structure of symmetries. It also admits soliton solutions. And what are solitons? Where they're localized traveling waves that interact with each other sort of in a particle-like way. It has an infinite number of conserved quantities, and it also admits a lax representation. So in a sense, as you heard that earlier today, it can be written as the compatibility condition between a system of linear equations. So all these properties, together with many others, of course, indicate that the Sinch-Gordon equation is integrable. Right, symmetry. So I mentioned symmetries earlier. It's easy to find some symmetries just by inspection. So you can see that we can see that the equation is invariant under translations in the z and z bar direction, and also it remains invariant under rescaling of the z and z bar variables. So we'll use this second property to perform a so-called reduction to the equation, to the Sinch-Gordon equation. So if we set v to be equal to z times z bar, and then w to be the exponential of the Sinch-Gordon field, then the Sinch-Gordon equation transforms into this one here, which is an ordinary differential equation. So we've managed to reduce a PD to an OD. Well, this is a very famous ordinary differential equation. It's called the Penlevet-3. I won't say anything else about this. There are specialists in the audience that know more. So we'll use this, the Penlevet equation, to find asymptotic solutions to our Sinch-Gordon field. So if we study the OD, so the Penlevet 3, we can find a specific asymptotic solution to this one, which takes this form. And then by using this, we can find the asymptotic solution, an asymptotic solution to the Sinch-Gordon equation. So, and this takes this form. So phi goes as log z, z bar. I forgot to say that it's when z and z bar are small. Right. Well, this is nice, but how can we make the connection to quantum integrability? So we'll start off by studying, again, as I said, the Sinch-Gordon equation, where here I have w and w bar instead of z and z bar. And we will apply this change of variables and also this transformation to the field. So if we do that, then the Sinch-Gordon equation transforms into this modified Sinch-Gordon equation. And this function p of z takes this form, where m and s are just some variables. So we will be interested in a solution, in an asymptotic solution of phi that is characterized by this behavior. So as previously, we want phi to go as log z, z bar when z and z bar are small. And we also want the same type of behavior when z and z bar are large. And L and M here are, again, as I said, parameters. So the modified Sinch-Gordon equation, like the simple Sinch-Gordon equation, can be written as the compatibility condition of this system of linear equations, which is also called the lax pair. We can write these, so if we write the solution psi, capital Psi, as psi1 and psi2, we can rewrite this in this form. And this lambda is the so-called spectral parameter. So we can write a general solution by using the lax pair representation. We can write a general solution psi to the linear problem, which is this one. So this is psi1, this is psi2, and I've just, so here I have psi and psi bar, and I mean psi comes from the, when I take the z derivative, the derivative with respect to z, and this is the derivative with respect to z bar. And what's very interesting and nice is that these functions, psi and psi bar, satisfy these ordinary differential equations, where here I still have a partial derivative, but we can think of this one as an ordinary differential equation if we consider z bar to be a parameter. So what's very nice is that actually these potentials, the potentials of these two ODEs have these forms. So we can see that the Sinch-Gordon field is actually a part, so this U, the potentials, depend on the Sinch-Gordon field. Okay, so as we said earlier, we will be interested in specific asymptotic behavior. So we take, when z and z bar are small, we take phi to go as log z, z bar. So when we take this solution, then the potentials of the OD, so I will consider the first one here. So then the potentials take this form, where I've performed this change of variables. So x is related to z, and E is related to the spectral parameter and to this parameter S. So the first ODE can actually be written in this form, which is the Schrödinger equation with this anharmonic potential here. So why is this important now? Why is it important that we manage to do this reduction and recover the Schrödinger equation? Because this Schrödinger equation appears in this so-called ODE-IM correspondence. What is that? So it's an interesting correspondence that was recently, yes, not too long ago. It was discovered, let's say, between certain ordinary differential equations defined in the complex plane and certain quantum integrable models in 2 dimensions. So these models, so the quantum integrable models, are spin chain-like models, and these models are used to describe the behavior of magnets, of magnetic systems, because we have the spin variable in there. And this link between the ODEs and the quantum integrable models is actually based on functional relations that appear in both sides, both in the ODE and the integrable model side. So we'll start off again by this Schrödinger equation with this anharmonic potential we recovered from the Sinch-Gordon equation. And so as I said, this is the potential term, this is the energy, and X is allowed to be complex. And we will be interested in finding the spectrum of this equation. More precisely, we are interested in those energies, or in those eigenenergies, for which there is a solution that decays when X is large and behaves like this when X goes to 0. Based on the first condition, so looking for large asymptotic solutions, the ODE can be found that it has a unique solution, a unique asymptotic behavior that's written like this in a specific sector of the complex plane. Based on this solution now, on this asymptotic behavior, we can define further so-called rotated solutions which decay in different sectors in the complex plane. So, and we define them in this way, where omega is this exponential factor here. And since the functions decay in different sectors of the Stokes, of the complex plane, we can say that they're linearly independent because each of them decays in a different sector, K. I guess it's easier to understand that if you consider this picture here. So if you have a solution that decays here, then you can write it, so this is psi 0, you can write it in terms, well actually here I've used -1, so you can write the solution that decays here in the basis of the solutions that decay here and here, so in this way. We can transform this relation into this one here, just by taking Wronskians between solutions on both sides of this equation. So T tilde is the Wronskian between this solution and this solution, and then T is the Wronskian between psi -1 and psi 1. So T tilde is, by definition, it's -1, so we can get rid of it and end up with this relation here. On the other hand, for small x, we can write a solution to the Schrödinger equation. So I've used the letter chi here. We can write it like this, and then combining the two asymptotic behaviors, so checking the solution at 0 and the one at infinity, and by writing the Wronskian of the solution at infinity and at 0, and by denoting this as Q, we can write this functional relation here. Why is that important? Because this is the so-called Baxter's TQ relation, and this functional relation here appears in the study of the quantum sign Gordon model, or if you want to say the 6-vertex model, or the XXZ spin chain. So essentially, this is a way we see that this functional relation here, which involves, I forgot to say that T's and Q's are actually spectral determinants. So they vanish at the eigenvalues of the problem, because we've considered the problem at 0 and at infinity, and the Q's are 0 for this eigenvalue problem in the eigenvalues of the problem. So this is very important because it shows a way of connecting a classical integrable model. We go to an ODE, and then this ODE is related to this functional relation, which has to do with a quantum integrable model. Well, a few words about what I'm doing now. I've been looking on the A2 system of the modified total field equations, and by imposing this specific asymptotic solution, we can find a solution, as I said, to the linear problem. So, and then by checking the solution at 0, combining the solution at 0 and the solution at infinity, we recover this linear relation. And these Q functions that appear here, similar to these Q functions. Are the Q functions of a two-dimensional massive quantum field theory associated to this Lie algebra SU3, and that's really important, and that's the new thing actually, because we've managed to associate a classical integrable equations with massive, this time, quantum field theories, because it was only done for massless quantum field theories. And that's more or less it. So just to give you again the whole story, we started from a classical equation, the integrable Sinch-Gordon model, by using a specific asymptotic solution to this model. We then use this asymptotic solution and we use it in the Schrödinger equation that can be recovered from the linear problem, from the Lax pair. And then from this Schrödinger equation, we can go on and make a connection to quantum integrability using this ODE-IM correspondence. And that's more or less it.
Other questions? So there's a wealth of known solutions to some of these Sine-Gordon equations and all this. Do they help you with your quantum integrable model solutions, or give you some ideas about how you might solve them?
We're actually only interested in this type of behavior, because by using this specific asymptotic solution, we can recover this specific Schrödinger type of equation with this specific potential, and that's what we need to then make a connection to the integrable model, because we're looking for these ordinary differential equations that appear in this correspondence. So I've only looked at that.
Yeah, I understand. Other questions? I was wondering if you can give some physical intuition to this system, right? Because you started out with this system with, I guess, objects on a line or something that are, was that a repulsive thing? I mean, just give some physical intuition. Is there a physical intuition that you can give to your motivating question?
Physical intuition. So actually,
the TOTA system you started with, right?
Yeah, so essentially that's a connection between the classical Sinch-Gordon model and the quantum sine. It turns out that it's the quantum sine-Gordon model. So, and this quantum sine-Gordon model, you can think of it as the continuous limit of a vertex model. So you have spins on a lattice, and you study their interactions, their behavior, let's say.
Okay. Is there a way to connect these sort of physical systems? Is there a natural way, or is it sort of remarkable that these things end up being connected even though there's not an obvious?
Well, I think the remarkable thing is that this classical and quantum connection through the ordinary differential equations, because this ODE-IM correspondence is I would say new thing, and it's quite curious that it actually happens. Mm-hmm. That you have ordinary differential equations that have nothing to do with a vertex model, a quantum integrable system, and just that's the interesting thing here. And I would like to say that so this type of potential here, it's motivated by things they study in string theory. Mm-hmm. So that's why this potential has been chosen. Well, I'm not sure I can tell you more about this. But I know that it appears in the study of in string theory.
All right, if not, let's thank the speaker again.